We begin chapter 5, and homework is so important in this class. That's why it always starts as the first slide in every chapter. You do need to do it because looking at notes is not learning. What you need to do in Gen Chem is work problems and think about problems and ask questions about problems. So why do we need to have this energy background? Well, I've got to convince you. When we get to chapter 8, you'll learn about lattice energy. Later in chapter 8, we'll learn about covalent bond strength. In chapter 11, we'll learn about all types of enthalpies of fusion and vaporization and vapor pressure. When we get to chapter 13, it'll be heats of solution. And finally, all of energy is wrapped up in thermodynamics in chapter 20 in chemistry 1220. So what you're going to have to learn to do in this chapter is produce this diagram. It does look like a daunting task, but I know that you can do it. When we get to chapter 8, you will start to produce this type of diagram, and it's what a chemist or a scientist uses to understand the energetics of a process. So, a little bit of energy history. Lavoisier was the first one to look at energy, looking at what comes out of a steam engine. And he felt that there was a caloric, and it was his theory, and he said that it was heat, and heat was a fluid. Well, Rumford followed during a war, and as he bored a cannon, he saw water became hot, so water was a fluid, so people accepted this as what was energy. Now, Carnot kind of put a wrench into it because he worked with gases and he looked at the compression and expansion. So here we had people talking about fluids, we had people talking about gases, but the person whose idea is the one that we accept today is Joule. And Joule looked at water temperature changes, and from that he was able to come with the Joule, which is a kilogram meter squared per second squared. It will be a conversion factor that you will use in a problem. So I kind of divided this into two pieces. On the left is what you already know. You already know that kinetic energy is the energy of motion. That's why there's the person on the bicycle. You know that potential energy is the energy due to position. So as a person leaves a hill, they have a high potential energy, and as they're standing still, a low kinetic energy. As they go down the hill, their potential energy is going to decrease, and they're going to see an increase in kinetic energy. So that's what you're bringing into our class. What I do believe will be new to you is this picture. So let's talk about what is it. There is energy on the y-axis, and there is distance on the x-axis. And what you see are little balls that represent ionic charges. Let's say the red is a positive, let's say the blue is a negative. And you have two different distances, and what are their energies on this diagram. So when the balls are close together, the positive and negative charges, the energy is going to go down. When you have two like charges and you try to put them together, the energy is going to repel. So to me, I don't know, I think they should have put this picture right here, they should have made this be a little bit higher, because this on the left is the smallest separation, the greatest attraction. Here, it should have moved up because here they say less attraction and a higher, less negative energy. So we're going to talk about this a little bit more, but before I move on, I want to say ionic substances, they have what is called electrostatic potential energy. If you have a different version of our text, they continually change the symbol for this. When we get towards deeper into this chapter, we'll talk about molecules, and they have bond energy. Bond energy is symbolized by the letter D. So I guess this chapter is really to introduce you to college level general chemistry energy. All right, let's just a little bit further. Let's talk about actually section 5.1 called chemical energy. The most important thing to pick up from this entire course is when you form a bond, energy is going to be released. And we're going to go deeper into this, but again, this is an introduction. When a bond is broken, what you need to do is energy needs to be consumed. And that concept will be developed during the course of this chapter, all right? Energy changes, they can be used in chemical reaction to transfer heat or to do work. And that's a tough thing to wrap your head around, but let's take it slowly. All right, here's that same picture, and it shows for charged particles ionics. And notice it says the electrostatic potential EEL will vary with separation distance. So here where they're close together, we have an energy sitting here. I still think this should be a little higher. We should have an energy sitting there. And by that I mean you read over to the y-axis, read up to the x-axis for distance. And you'll have some homework problems that will help you understand this better. The thing that you have to realize is we will have a positive energy for like charges. That will be positive. And you notice the two blue balls with the EEL greater than 0. And it'll be negative for unlike charges when we bring a positive and a negative together. So conceptually, and work some problems to better understand this. Energy, now, what you may be asked to do is to actually calculate this energy. And you will be given this formula. You will be given all the information you need. K is a constant. Q represents the charges, and if it's two unlike charges, it will work out to be a negative number. D is the distance between the ions. So what I have here is a lattice of sodium chloride, and what the distances are that you see given on the right are the radii of the sodium chloride and the chloride anion. And if you add them together, what you will get is the distance between the two, which is 2.83 angstroms. So let's do the calculation first. We will take the constant 8.99 times 10 to the 9th, and it is in joule meter per coulomb squared. We will multiply this by the Q. 1.6 times 10 to the minus 19 coulombs, one of them is positive. 1.6 times 10 to the minus 19 coulombs, one of them is negative. And we will divide it by the distance between the ions, which is 2.83 angstroms. Now here's where what comes into play from chapter 1 is used. We don't have angstroms, we have meters. And so what we have to do is we have to say 1 meter is 10 to the 10th angstroms. Now, in high school, you may have separated this all out. In college, we do it all in one line because our calculations get more complicated. When I multiply those numbers together, I come up with 8.13 times 10 to the minus 19 joules. And that would represent this point on the graph where we have made the lattice. If we were to separate the ions, our D would be increasing and our EEL would be becoming more positive. And as you can see, if I draw a line over to the y-axis, this value represents the 8.13 times 10 to the minus 19. As I go up, my value would become less negative. And that's really the take-home message here. I know it kind of feels like it dropped in from outer space, but that is how you would calculate the electrostatic lattice energy for an ionic solid. What's on my last slide? Well, this is an intro, and what we want to do is we want to relate the changes in energy, the delta E's. We're going to talk about that in this chapter, and we want to relate it on the molecular level. In 1210 we just begin, in 1220 we go a lot deeper. And there's chemical energy. And that's due to the potential energy that's stored in the arrangement of the atoms. You could say that it's an ionic or a covalent bond. And as you undergo a chemical reaction, the bonds rearrange, and you will either need energy or give off energy in that process. Now, the other point to make here is energy is possessed because of temperature, which is a thermal energy. And that's associated with the kinetic energy of the molecules in a substance. We'll use this again in the gas chapter. We introduce it here. And in your mind say, when I see a temperature, that reflects the motion of objects. Think of a solid, think of water, 0 degrees centigrade. All of the water molecules are bound in a lattice. When I have a liquid, let's say at room temperature, I just said room temperature, the molecules are able to move around. And when we have something like steam at 100 degrees, the molecules are really moving. So you know what water freezes at and boils at. What I'd like you to do is start to build an understanding that temperature does give you a relationship of the motion of molecules.